Welcome back, everybody. Let's continue. So we were here looking at variable length encoding, again, with the idea that every packet has 8 bits. That's one example. We only use 7 bits to encode the actual bits of the integer, and the first bit is special. It tells you doesn't end here or ends here. Note that this is a convention. You could also do a 1 for doesn't end here and a 0 for ends here. It really plays no role here. Here, you just use this convention. Okay. And so on and so forth. So if you have an integer in base 2 like this, all you need to do is add back the zeros everywhere and the 1 at the end. Okay, so these are examples. Here, I'm not using packets of 8 bits at 4 bits instead. That's the parameter of the encoding, so I can do whatever I want. So if now I use packets of 4 bits, then it means I have 3 bits for the integer and 1 for the 0 or the 1. So in that case, for 4 bits, then between 0 and 7, the 3 bits are enough. So I just put a 1 in front because that's the one and only packet, followed by the 3 bits with the binary representation. And then all the way from 8 all the way to 6, I have to think. That is 2 to the power of 6, that's 64. 7. Okay. When my brain is freezing when I'm in front of public, so I cannot do live computation. But anyway, if it fits on 3 bits, then you can just continue all the way like this. Yes, it's all the way to 63. That's why I was wondering if there's an offset, but no, there's no offset. So all the way to 63, 2 packets, and so on and so on. It gets bigger and bigger and bigger. So you see that the variable length encoding is elastic. It grows as you get higher and higher and higher numbers, it keeps growing. That's perfect for the encoding of our gaps, right? Because it means that for the small gaps, we are only going to use very few bytes. And when the gaps grow bigger and bigger, we are going to use more. But now it's more efficient than having exactly the same number of bits for all gaps, right? So this is why it's some progress, right? Here we save 50% less space, roughly speaking. We call that encoding parameterized because you can vary that parameter. In the first example that I gave you, there was 8-bit packets. In this example right here, it was 4-bit packets, but you could do it with any number. Well, maybe n equals 2 is a bit ridiculous, but 16, 32, I mean, you can increase the size of the packets. Okay. By the way, we'll see that n equals 2 is actually not that ridiculous, but done right. I will come back to that. Okay, so here, if we have this huge sequence of zeros and ones, and I don't tell you where it starts and where it stops, if I tell you that this is based on 8-bit packets, then now you can separate, because since you know it's 8 bits, you just need to look at the zeros and the ones in here, and all the ones tell you that it stops, all the zeros tell you it doesn't stop, and now you can actually reconstruct. By taking the parts, you just throw away the first bits, right? Then that gives you the base 2 representation of the integers, and then you can decode them, right? Who is with me? Okay, so you can encode and you can decode, but the power of a prefix code is that when you decode, you even decode where it starts and where it stops, thanks to this extra information. Okay. So again, there is no free lunch because yes, you compress, you save a bit of space, but you have extra work to do to decode the whole thing back to the original numbers. Now, when is that actually important? It depends. Because there are several reasons why we compress, several reasons. One of the reasons is to gain on disk space. Now, if this is all we worry about, then it doesn't really matter how fast, of course, without exaggeration, but it doesn't really matter how fast the decoding is, because typically the cost of writing and reading from disk is larger, right? So if you just are interested in using less disk space, then it's less of a pressure to be efficient. However, if the goal of the encoding is to do things faster in memory, to cache more, and so on, then it actually becomes important, right? So its performance matters a bit more, right? So this is the idea. You can also vary, here you can vary the parameter of the encoding, which is the size of the packets. So if you have enormous packets, you might not get that much compression, but it's also easy to decode. If you have very small packets, that might compress a bit more, but there's a lot of bits to manipulate because you have more packets to reassemble back into the binary representations. Okay. Can we compress even more? So now that's the part where I told you n equals 2 is ridiculous. Well, technically, when you start saying n equals 2, you're kind of saying you don't want to deal with packets or bytes anymore. You really want to work on the bit level. You really want to have elasticity, not just in terms of packets, but really in terms of the bits themselves. Can we compress even more? Obviously, yes, because otherwise I wouldn't be standing in front of you. So yes, we can compress even more. And that even more has a name. It's called the gamma encoding, the gamma codes. This is because of this person, Peter Elias of MIT, who invented that code. So this is why it's also known as the Elias gamma code occasionally. And I'm going to now show you how the gamma code is actually working. But there is a prerequisite to the gamma code. I need to show you another code before that. That code is called the unary code. It's actually incredibly simple, and it's going to be even simpler if I tell you that it's also known as the thermometer code. Because the way you encode an integer, like 12, is that you are going to write that many ones, 1, 2, 3, all the way to 12, and then a 0. That is the thermometer encoding. Why? It's like a thermometer, right? The higher the integer, the longer the strings of ones is, and you just look at it like a thermometer. So this is the unary code. Who would be able to encode and decode any number with that code? All of you, right? So it's relatively easy. Now you might think that's not very efficient, right? Because that takes a lot of space. And you know, whenever you deal with algorithmic complexity, Turing machines, and so on, and you look at the efficiency of prime factor decomposition and so on, typically you look at numbers written in base 2, right? And then you look at the number of bits that it takes. It's the logarithm of the integer. But here it's awful because this is not the logarithm; it's the integer itself, right? So that's really, really bad in terms of space wasting. Nevertheless, this code has properties that make it useful as part of the gamma code, right? So this is why I showed it to you. It will actually come back because it has nice properties that I will show you later. A question though, who sees that this is a prefix code? Great. Prefix code, remember, means I know where it starts and where it stops. So if I put plenty of thermometers next to each other, if I put plenty of integers and code it that way, how do you tell where it stops? Well, just look for the 0, right? That's how you know where it stops. So it's a prefix code. So important property. Okay. Maybe I'm too far away from the receiver. Yeah. So yes, this is what I just told you. It's just a bit slow somehow when I press, seems to be, yeah, 12 ones because you're encoding 12 and then the 0 to mark the stop. Okay, so this is the encoding, the thermometer encoding of the first integer, right? 0 is just a 0 and so on and so on, okay? And now the proof that it's a prefix code, again, you look for the 0 and that's how you decode the prefix codes. Okay. Now that we know that, let's talk about the gamma encoding. So the gamma encoding is a way to encode any integer as a sequence of bits in a very elastic way, but at the level of the bits, not just in packets, but at the level of the bits. Let me directly tell you how that goes. The first thing you do is you express 19 in base 2. So 19 in base 2 is 10011, right? 16 plus 2 plus 1. So 10091. What do you do next? You remove the leading one, there's always a leading one, right? If you except for 0, but if it's not 0, there's always a leading one. So you just remove the leading one and just consider the rest of the number. You still have enough information because you know there's an implicit leading one. And what you do is that you encode the length of that string. So here it's a length of 4. There are 4 bits in there. So we encode 4 with the thermometer encoding, with the unitary encoding, so 1, 1, 1, 1, and then a 0. And then we concatenate, right? So this is the gamma encoding of 19 looks like this. Another way, if you want to explain it even faster without the thermometer encoding, you basically take the base 2 representation without the leading one, then you add a 0 and you add as a mirror, right? You add as many ones here as they are here. So how do you recognize a gamma code? There's always a 0 in the middle. On the right, you have the base 2 representation without the leading one. On the left, you only have ones. Right? That's the gamma code. For whom is that here? Okay. Who would be able to encode and decode the gamma code? Okay. So now let's do it for the first integers. So the first 4, so 0, 1, 2, 3. In binary, this is what it looks like, 0, 1, 1, 0, 1, 1, and so on. The binary without a leading one, when for 0 and 1, it doesn't really make sense. These ones are a bit special. 2 and 3, we just remove the first one. The length is 0 or 1. Then in unary code, it's 1, 0 for 2 and 3. For, again, 0 and 1 are special. And so the gamma code for 2 and 3, that would be 1, 0, 0 and 1, 0, 1, right? Now, what about 1? 1 is just encoded as a 0. That's it. Just a 0 and nothing on the left and nothing on the right. 0 is not encoded at all. So what happens if you want to encode non-negative integers, including 0? But all you need to do is offset by 1. Right? So instead of encoding n, you encode n minus 1, and then you no longer have the gap, right? So this is basically an easy fix. But the regular encoding cannot encode 0. It's just starts at 1. Okay, let's look at the next ones. So 4, 5, 6, 7. So these have 3 digits in base 2. It means that if you remove the leading one, there's 2 of them. Then you have 1, 1, 0 as the thermometer encoding, and you get these on the right. Who agrees with this? Okay. And so on, all the way. And you see that it keeps growing. Do you notice that the length of the gamma code is always odd? Who sees that? Right? Because there's the 0 in the middle, and then plus 2n, right? So the number, as many bits on the left and on the right. So if I give you an encoding that has an even number of bits, you can already say that's not a gamma code. Cannot be. Okay, and if it's not a 0 in the middle, you can also say that. Note that there are also people who have the opposite convention. They use a 0, instead of 1, 1, 1, 1, 1, 1, 1, 0, they say 0, 0, 0, 0, 0, and then 1, right? It's only a matter of convention, really, the way you do it. Okay, so that is the gamma encoding. So it has properties. It's variable length, it's elastic, right? It goes from just 0 for a gap. Remember, we encode the gaps, right? So it means that when you have a gap of 1 between 2 postings, it needs a single bit, just a 0. And that's it. So the gaps of 1 are extremely efficient to encode. This is also why you don't really need to get rid of stop words anymore, because this is incredibly efficient. It's a prefix encoding. How do you know it's a prefix encoding? Well, look, if you start reading it, just count the number of ones until you find the first 0, and that tells you how many more bits you need to read, right? Who sees that it's a prefix encoding? Okay, so that's part of the magic of that code. And it's a universal encoding. Now, that I haven't explained yet, so I will have to explain to you what is a universal encoding. For this, we need to go a bit into information theory. Who has already a bit of information theory knowledge? Some of you. Who doesn't? Okay, let's do a 101. I'll not go very deep in it. I'm also not an deep expert of information theory. But basically, there's somebody called Shannon who first formalized this in a very clever way. Information theory is really all about channels. You always have two people who try to communicate, and then the first person tries to send over information over the channel. But you know now that the way we send information in a digital world is with zeros and ones, right? So information theory is all about saying what's the minimum number of zeros and ones that I need in order to transmit such and such information. It's all about this. And this is what the Shannon entropy is actually measuring. The Shannon entropy tells you how many bits you need to send. Now, there's probabilities involved. It's not something that is just absolute and deterministic. There has to be a bit of probability. Why am I saying that? Because if it's deterministic, you don't need to say anything, right? If you're saying something obvious, like, I don't know, blue is a color, there is nothing to send, right? Because everybody already knows that, right? Or cats are funny, right? You don't need any bits to encode that. The reason why you would need bits is that there is a bit of an unknown, and an unknown typically is associated with a probability distribution, right? That probability distribution encodes the uncertainty, right? It would be certain for the probability distribution that is probability of 1 for a value and 0 for the others, but if it's not the case, then there is a bit of uncertainty. Now, the way that this is modeled is with random variables. We will come back to a 101 just to make sure to refresh you on random variables in a few weeks when we do probabilistic information retrievals. But basically, a random variable is a probability distribution over some values, right? So you have integers. So let's take the whole set of integers. And every one of these integers can come out of the pipe right there. This is a source that emits integers. And every integer has a specific probability of coming out of the pipe, right? For example, you could say that 0 has a probability of 1/2, 1 has a probability of 1/2, and all the other integers have a probability of 0, right? That would give me a random variable that I can call x. And it's associated with a probability distribution that I can call px, p subscript x. And that's a function that takes an integer and gives me the probability that it has to come out of that source. Now, if Alice tries to ship over to Bob the integer that she got from the source, then she will need a few bits because the source is probabilistic. So Bob cannot know. And then the question is, for some probability distribution over x, what's the smallest average number of bits that you can possibly achieve? And here we really have to take into consideration that Alice is free to encode the integer in any way she wants, right? You can just pick any strategy to encode your integers any way you want. And the question is really, what is the optimal strategy? And the finding of Shannon is that there is a lower bound, a theoretical lower bound. Like if I give you a specific probability distribution, I have a way to compute a value that is the lower bound. And I can say with absolute certainty that there is absolutely no way on Earth that Alice is able to communicate to Bob with less than that number of average bits. This is called the Shannon entropy. Okay. So again, we try to transmit them, compress them as much as we can. Lossless. Lossless means we cannot lose information. So Bob must be fully informed of the integer after it has been sent. Okay. If I come back to my example with 0 and 1 with a probability of 1/2 and all the others with a probability of 0, the entropy of that is 1 because you just need to ship 1 bit and then, and this is optimal. Okay, now a bit of theory. I'm going to try to not scare you away with that. The Shannon entropy is typically denoted with a capital H. Capital H is a function. What does it associate to what? Well, it's a function that associates a random variable with a real number, technically a non-negative real number. In quantum physics, it can be negative, but here it can't. So we associate a random variable with an integer. You gave me any source like this, the one on the top left, a probability distribution source. I can associate it through that function h with a real number, non-negative real number. Okay, how do we compute that? It's actually computed as the expected value of something. It's computed as the expected value of the amount of information that every integer can carry. I is a function that takes an integer. For every integer, it can tell me the quantity of information that it has. I depends on the random variable, of course. Now, this is the kind of formulas that can quickly give headaches, and it also gives headaches to me. Why does it give me headaches? I will tell you why. This is because the way we use the capital X, it kind of depends on the context, and that has to do with how long we want the formulas to be. Because when I use H really takes the random variable itself as a value, right? X is really the random variable. But I takes an integer, so it's really an integer passed to I. So when I have a random variable X and I apply I, which takes an integer, that gives me another random variable, and then you can take the expected value of that variable. But it might be clearer if I actually explicitly write it down like this function. So I typically is minus the log in base 2 of the probability right here. And now you see this px, that's my probability distribution of the random variable. And you know that a probability distribution, that's a function that takes a possible value as input, right? So the input of px is an integer. But if instead of the integer, I put the random variable itself, that's just a shorthand in math of creating another random variable. Right? For whom is that clear? If it's not, don't worry, I'll come back to random variable in just a few weeks, right? So basically, maybe it's even clearer if I write it in this way. So now I really wrote the small x, right? I vary x with all possible integers that it can take. And basically the Shannon entropy function is minus the sum of p log p, basically of all the p log p for the variable x. So that gives me the entropy. Now, I know that for those of you who already knew that, it's easy. For the others, it's not. So I came with visuals and illustrations and examples and so on to make it even easier. So let's take a deterministic distribution and just put that formula in there. So it's really an iteration over all integers. And for every integer, I compute p log p of that integer for my probability distribution. And then I sum over all the integers. So let's do it. It's really a purely mechanical thing that we do here. I have a deterministic distribution. What is my probability distribution? Well, it's 1 for 0, and it's 0 for all other integers. So they don't even exist. Now, if I compute my p log p, p for 0 is 1, right? It's deterministic. Minus log p, so that's minus log 1. You know that log 1 is 0, right? What about the other p log p? Well, p is 0 for the other integers. So p log p is always 0 for the others. That's why they don't appear. Now, if I compute minus p log p, it's 0 times 1. That gives me 0, right? That's the whole sum. But again, there's only one integer for whom that's not 0. So this is why we only have a single term. Now the entropy is 0. When in fact, that's always true. A deterministic distribution always has an entropy of 0. But in fact, I've already told you that. I told you that if you want to transmit an information to Bob that he already knows, then you don't need to send anything. And that's what we say when we said the entropy is 0. It means 0 bits are needed to transmit something that everybody already knows. But it becomes interesting when you actually do have uncertainty. So when you have a probability distribution that is no longer deterministic. So let's pick an example. Now I'm going to consider the probability distribution that you see visually with 0, 1, and 2. And after 2, it's all probability of 0. So let's say 1/4, 1/2, 1/4, right? 1/4, 1/2, 1/4. It sums up to 1, right? These three sum up to 1, so it's a probability distribution. 1/2, 1/4, 1/4. Now, let's blindly, without even trying to understand it, I just plug this p log p, the minus p log p in there. So the minus log p of a quarter is 2, minus log p of a half is 1, and minus log p of a quarter is 2, right? Now I multiply this times this, this times this, this times this. So that gives me the minus p log p's, right? 0, 5, 0, 5, 0, 5. And I take the sum. Again, that's my sum right here. I sum over all possibilities. That gives me 1.5. What does that tell me? It means that if this is my source, so this here is the probability distribution of that here, the source that gives the integer that you want to ship over, if this is the source that I'm using, then I just plug into it all the values into my huge Shannon entropy formula, and it spits out this 1.5. And the 1.5 that it spits out tells me, on average, there is no way that Alice is ever going to do better than 1.5 bits on average per integer that she's going to set. This is what the Shannon entropy tells me. She can do it with 2, with 3, with 4, but not with 1 or not with 0, right? It cannot be smaller than 1.5. This is extremely powerful. It was a major discovery that, that Claude Shannon made, right? So you don't need to go this formula with the P log P. Everybody who did information theory knows it by heart. You don't need to. You just need to know that it exists. There is a formula, a magic formula that takes a distribution and spits out a number. Okay, that's what you need to know. Now, let's do it with yet another distribution. Now, it's a uniform distribution. 4 integers, 0, 1, 2, 3, all the others are 0. So that is obviously 1 over n, right, for the uniform distribution. So now I have 1/4, 1/4, 1/4, 1/4. Now I blindly put the formula in there. So the minus log of that, it's always 2, right? Minus log of 1/4, that's always 2. Now I multiply it, 1/4 times 2, 1/2, and I sum over that, it's 2. So if I zoom out, I have a uniform distribution that can spit 4 possible integers, each with equal probability. The Shannon entropy tells me the best you can do is use 2 bits to ship an integer. What does it mean? It's kind of natural, right? How do I encode it with 2 bits? 0, 0, 0, 1, 1, 0, 1, 1. That's the example. So it's something that is very natural for the uniform distribution. Yes? No, fully general. Doesn't have to be a prefix code. Oh, that's a good thing. That's a good question. So it might be true that there is a concept of that there is the concept of knowing where that stops. That's a very good point. Yeah, I'm myself not a big expert in information theory, but yes, you might have a point. But I think the way it's explained, yes, go ahead. My question is, only one of those numbers in that is gone. Yeah, so my recollection, so, oh, you don't have the microphone, so let me explain and then I'll comment. The question is whether what it has to do with prefix codes in the sense that you could use your channel, your transmission channel, by shipping just a 0 or just a 1 or just 0, 0 and 0, 1, for example. As far as I recollect from what I learned of information theory, the trick here is that sending something and then stopping, the stopping is also information. So the stopping is also a bit, kind of, which basically, in other words, means the prefix code interpretation. If you consider that stopping is information, I think it would be equivalent to basically require that it's a prefix code. Because the prefix code, when you have a prefix code, the information that it stops costs 0 because of the prefix code. So if I look back to your question, yes, you are right. It needs to be a prefix code for that reason. Yeah, very good point. Thank you. It's going much more into details of what I wanted, but this is very good. Okay, so this should be kind of intuitive, right? If you have to ship 4 possible integers equally distributed, just use the encoding 0, 0, 0, 1, 1, 0, 1, 1, and that takes care of it, right? What about the geometric distribution? Well, the geometric distribution means that you divide the probability with 2 every time. So 0 has a probability of 1/2, 1 has a probability of 1/4, 2 of 1/8, and so on, and you just go like this. And you know that it sums to 1, right? If you sum all of the negative powers of 2, you get 1. Who knows that? Right? Okay, so it sums to 1. This is a probability distribution. It's called a geometric distribution. It's technically the distribution of the number of times you need to toss a coin until you get heads. That's the geometric distribution. So we can compute the entropy of that distribution, which is well hidden behind the toolbar in the lecture hall. You already see it on Zoom, but here you don't. There you go. If we do the whole math and feed that probability distribution inside H, we get 2 out. So it means that the entropy is to, on average, you will have a prefix code encoding of the integers. The best you can do is on average with 2 bits, right? Okay. Now, until now, we computed entropies, right? We computed that function H. Now, when we look at a specific encoding, the unary encoding, the gamma code, the variable length encoding, and so on, what we are interested in computing is the expected value of the length. So it means that instead of computing this minus log p, I will instead compute the length, right? So if I use a variable bind encoding on 8 bits, for all the first integers, it's going to take 8 bits, and then after a while 16, and then 24, and so on, right? So we compute this expected value. You know how to compute an expected value, right? You multiply each possible value with the probability and sum over that, and that gives you the expected value, Erwartungswert. And if we do that, we find that the average length of the variable byte encoding gives me a bit more than 8. It's not exactly 8 because there will be 16 and 24, but it's still 8.00 something, right? How do I know that everything is okay and the world is in order? Because that here is larger than the entropy. And the Shannon, basically the fundamental theorem tells you whatever encoding you pick, you compute it average length. Shannon tells us this number right here has to be larger than that. It is absolutely not possible for us to find an average length that is less than that for any encoding. That's what we learned here. Okay. Now, if we do it for the gamma code, so I still have my geometric distribution, right? For the geometric distribution, now I compute the length of the gamma code. So you remember that for the first one, I offset by 1, right? Because here I want my 0. So I shift the gamma code by 1, as I told you earlier. So you remember that the 1 is split with a 0, and then it's 1, 0, 0, 1, 0, 1. Then there's 4 integers with 5. It's always an odd length for the gamma encoding. So what if I feed that in there and compute, then I find something like 2.266, right? It's the same probability distribution. What that tells me is that the gamma encoding for that distribution is doing a better job than the variable byte encoding, because the variable byte encoding costs me 8 bits on average. The gamma encoding costs me 2.266 bits on average. For that distribution, if I change the distribution and I get something else, but for that distribution right here, then it is the case that the gamma encoding is doing better than the variable length encoding. If I change the distribution, of course, I might get something different. It might be that for some distribution, some encodings are better, and so on. In fact, there is, let me ask you a question, because that's actually a very interesting question. No, not this one yet. It's actually something very surprising that I would not have thought. I have to find it again. I would not have thought. You remember this thermometer encoding? You would think there's nothing less efficient than that, right? It takes a huge number of bits to encode an integer and so on. There's no way it can be optimal. And in fact, I'm asking you, could it be optimal for one specific probability distribution? Is there a probability distribution for which the unary encoding, the thermometer encoding, is optimal? So what do you think? Let me start the quiz. So answer A, it's never optimal. There's no way the unary encoding can ever be optimal because it's so inefficient. Or is it optimal with a Poisson distribution with lambda equals 1? Or is it a very binomial distribution? Or is it optimal for any distribution? I think there might be more answers. There has to be, because I know that, yeah. Negative powers of 2. I'm sorry, I gave away the right answer, but anyway. So what do you think? When is the unary encoding optimal? All right. And in fact, it is the negative powers of 2. In fact, the negative powers of 2, that's the geometric distribution. That's the one we've just seen on the slides. So let me get back to the slides. If I did it correctly, we should be exactly where we were. Yes. So, yeah, great. Can you believe this? Look at this. We compute the average length of the unary encoding for the geometric distribution. We find it equal to 2. Well, we know it cannot be less than 2 because I told you the entropy is 2. So the entropy gives us, oh yes, because I reopened the slides. The entropy is 2, so it cannot be less than 2. But here we find 2. It is optimal. That's as good as it gets. So it means that if the integers that Alice wants to ship to Bob, if they follow this geometric distribution, for example, because you generated it with tossing coins and counting the number of coins you got until health, then encoding with the thermometer encoding is optimal. That is, in fact, very surprising because you wouldn't think that it could actually be optimal for anything, but it turns out that it is. So if it follows that geometric distribution, then you encode your integers by 1, 1, 1, 1, 1, 1, 1, as many as integers, then a 0. And that is, in fact, optimal. But what's very important to understand is that this is tied to the distribution of the source. If you change the distribution of the integers, it completely changes the average length. It completely changes the entropy, right? So this here is another geometric distribution with, instead of powers of 2, it's other kinds of powers, but it's always optimal. So the unary encoding is always optimal when it's a geometric distribution. And it turns out that for this other distribution, the uniform distribution, then you see that the thermometer encoding has an average length of 2.5, which is less good than 2. So now you see it's inefficient. In fact, if you now take a uniform distribution over the first billion integers, then as expected, the average length of the thermometer encoding is absolutely awful, right? So here the average length it would take is half a billion. So this is basically showing you if it's the geometric distribution, optimal, but if it's pretty much any other distribution, it's absolutely awful. But again, the point I'm making is it depends on the distribution. Does it? Well, not for the gamma code. And now I'm getting back. Yes, you have a question? Yes. So the answer, so the question is whether we have to design the encoding depending on the distribution. In general, yes. In general, you need to know the distribution and then you design your encoding. That's kind of what you do with zip files and all these things, right? But, and this is kind of how I'm going to almost end the lecture today, the beauty of the gamma encoding is that the gamma encoding, whatever distribution you take, doesn't matter. It can be the geometric distribution, the uniform distribution, any distribution. The gamma encoding has an average length that is always upper bounded by a factor of 3 of the entropy. So whatever distribution you take, it's going to be less than 3 times the entropy. This is what we call a universal encoding. What that tells us is that the gamma code, no matter what distribution you have, is going to be asymptotically optimal. And that is an absolutely incredible property of the gamma code. You saw that it's not true for the thermometer distribution. Here it highly depends on the distribution, but the gamma code has that property and that kind of answers your question as well. If you're using the gamma code, then you don't care about the distribution. it's always within a factor of 3, a constant factor of that distribution. So this is why I showed you all these animations and information theory, because I wanted to tell you that the gamma code is a universal code, because no matter how it distributes, no matter how the gaps distribute, because in our case, it's the gaps that we want to encode, I don't care how the gaps distribute. I know that my gamma code is going to be optimal within a factor of 3 of the entropy, right? And now there's a few more digits here on how we are doing when you use them, but you see, this is a classical result that we basically diminish by 75%. So we are back to just 1/4 of the original size of the posting list, right? So this ends the lecture today. I'm just going to ask you if you understood what I've been telling you. But otherwise, we've pretty much done. Okay, so again, this information theory, this is obviously not an information theory course, so I don't expect you to know all of that. You just need to understand that there exists the concept of the entropy of a distribution, and that you can compute the average length of an encoding, and the gamma code has this incredible property that no matter what the distribution is, it's always within a factor of 3 of the optimal average length, which is the entropy. Okay, and it seems that I didn't lose you too much in spite of the information theory part, which is great. Okay, so now you can squeeze stuff on your laptop. It's a great thing. Any database person will tell you that squeezing as much data as you can on a single machine is an awesome thing to do, because it saves money, it's fun to do, you can optimize your code and everything. Thank you very much. I hope you enjoyed today's lecture. Next week, we'll do linear algebra. We'll look into vector spaces and how to encode the documents as vectors. So thank you very much. Thank you, Marco, for moderating. Enjoy the quiz of the week, which I think is graded, right? It's on the precisely on these encodings and how to compute them. Thank you very much. See you next week at 10 a.m.